looking at, is this the one where we are? Yes. Since there are, the issue is, since there are transitive dependencies, people were saying that no, this should be considered as 3NF. You know. I said it is not in 3NF, and then um, um, this is suddenly in 1NF, first normal form, because all the attributes are atomic. Okay, is it in 2NF? 2NF requires that. What is the requirement of 2NF? 2NF requires that second normal form. No non-prime attribute should be partially dependent on the key. Okay. Now, which are the prime here? The prime attributes are all the no. As you can see, this is a key. This is a key. This is a key for this, right? Given that any of this, you can completely, get the this thing. So all the attributes are prime attributes, right? Prime attributes being partially on side of the dependency, functional dependency. Every functional dependency, the left side of the functional dependency should be a super key. Okay, this is the DCNF requirement. Okay. Now to make things little more clear, every functional dependency, if you're taking this, every functional dependency, okay. Now what I'm going to show is I've put some functional dependencies, but more functional dependencies can be derived from this functional dependency, which I'm going to do in today's class. Okay. But whatever functional dependencies you start with, so this is a set of functional dependencies. More functional dependencies can be drawn out of it. Every functional dependency that the super key. LHS is the super key. AB is the super key. Okay. Now the question is, suddenly C is not a super key, D is not a super key. Okay. So suddenly this is not in BCNF. Okay. Because this requirement, now we can see why is this important requirement. If this is not a super key, there will be a duplication, because super key means that the value of that set, for example, if A B is called super key, there will be only one value of that which will be in this tuple. Instead of tuple that is called a R, there is only one value that will come in. And hence it is not going to duplication of the data or fact because of this dependence. Okay, once this is super key. Okay? Now every functional dependency in the super key ensures that there is no duplication of the information of the data required. For example, here we get this negative. Okay? Right? Now if you look at this state is a dependency in terms of what are the functional dependencies? Yes, the functional dependencies these are here. Adding more into this now. Compare with the functional dependency. This is the case of A. A for A and the origin, destination, zone, and variable. Okay? Every zone there is a many there. So given a zone, you can decide on the many things. So if we execute, you can see here this is functional dependence. Now if you look at this example, the train number is a key in record because train number is not going to be. So we know that train number is a record. Even train number, everything else is also dependent. So if you look at this train number and then get the closure of this train number attribute, you will get all the, because of this functional dependency, even train number, you will get the complete closure of the attribute. Okay, relating to this relationship. So train number is certainly the key for this relationship. Okay, but whereas origin is not the closure, origin is not a key until even origin is only a attribute that you can fix its node. But there are other errors, record, and hence origin is not key. Similarly, node is not key. So, if you look at these two functional dependencies, they will cause duplication. Okay? So, what DCNF is saying is every functional dependency should be reflected as a super key of the relationship so that none of these will cause the duplication. Okay, now you can see very easily. For example, here, Delhi decasing, origin city, Chennai South, Okay, similarly, here you can see same thing, Vizag South Central, Vizag South, okay, South Central, R and K. Okay. So, if every reflect, if every doesn't reflect as the key, the left side of the key doesn't reflect as a super key, this will cause duplication. So that's what DCNF is trying to say. Okay? The question is to we understand the DNF. Okay? I gave that definition, okay, where the idea is of DNF is we gave DNF definition. Okay? I'll give you that. That's not a problem. Okay? The DNF says that DCNF suddenly will not cause any problem of once a relationship between DCNF. Every FD, the left hand side of the FD is a super key and there is not going to be any duplication. There are rules that I gave, which is even more easy to follow. Let's say E equals E is same as the I think this is what the definition that we okay. Now, what this is saying is, if even though the LHS may not be a super key, in the take property of something.
We have system just I'll choose I
Okay, so I do know actually I can figure out now the G. I'm just trying to take the trying example. Okay? Now let me do it. This I'm doing it more like a whole thing. Okay? For example, let us say A is there is a functional dependency A to B, and then slide. No example. Okay. I think complications that we are avoiding. I think we are only trying to take more analysis.
Student వచ్చిందో
Slightly very confused with the
not all
Okay. What we are seeing is, okay, take this, okay. Now what this is saying is, the determining the attribute of C functionally determining A, right? Now AB is the key here. Okay, AB is key. Now this currently is not in BCNF because C is not the key for this relationship, right? But then, if you apply the rule that I gave for P and F, that the right-hand side is part of the key. The right-hand side AB, selling part of the key. Then we're going to say this is in P and F. Okay? Now we actually gave this relation, right? Why? Because if you split this for getting into region, the only way to split this is RB and then RAB and then RJC. Okay, that is the only split that is going to bring it into BCL. Okay, right? But the question is, many people have a problem with looking at the example that we have is to see if a transitive dependency is going to cause a problem. Okay? Transitive dependency, because of that, you actually have a, I think I'll take it two slides here. Then insert a slide. See, as I'm doing online, I'm actually messing up my slides. Okay? The two definitions of DNS, okay, which we are now going to look at. One definition that I use is for T, or RHS is part of T. Okay, this is one definition that I like that I will get. Then, third definition we have is if there is an undependent string, then they call it that it is not in PNN. That's probably not correct way of defining PNN. Okay? What it says is, if a key is transitively dependent, this is very important, transitively dependent. Okay? I'll show you how these two are saying. If a key is dependent on a non-time attribute, okay, then it is not in PNN. Why is this so? Okay, look at this relation, okay? Let us take the relation R. Both are same. Look at the strictly definition, the second definition. But that is what we are saying about PNN. Okay? Now look at this definition. Okay? Now let us say there is a dependency of A to B. Okay? In fact, I should do the action. A to B. Okay, then B to C, let us say. Okay? Right? Then we say A to B. Okay. Why I postpone this discussion, saying that I will look at the Armstrong actions for this part of the base. The reason is now, A is the key here to look at. Okay? Because A is constantly making A constantly dependent on C. Because A is functionally determining B, B is functionally determining C, means that A is also functionally determining C. So extra action that gets derived now, that's the dependency that gets derived now. Okay? As this. Right? Now A is a key for this. Suddenly A is a key for the relation. Okay? Because even A you can functionally determine all other things. Okay? means there is transitively determining a non-prime key, both B, C, D are non-prime. And only A is the key. B with C, but attributes are key attributes. Only A is the key for this relation. Okay? Given that A is the key, there is a dependency among the non-prime attributes. Okay? That is what PNF will prevent. So it's very important to understand this constant dependency is coming because of the functional dependency across non-prime attributes. Okay? This is certainly not it. If a key is functionally dependent to transitivity on the non-prime attribute, that is mainly because of the functional dependency. Since the non-prime attributes, suddenly look at the CNN definition. An LHS has to be key. This is never going to be there. Okay? Right? So it is also not good to be part of a key which is non-prime attributes. Certainly means the definition that I gave, the LHS has to be a super key. Sometimes you find in some books which actually comes because the QNF says that QNF finds that non-prime attribute good is partially dependent on the key. DNS says that the key attribute is not constantly functionally key to B. So, okay? Right? So this is what we mean by the transitive dependence. Why by definition of LHS in the super key or RHS is part of a key is important for you to remember. In fact, forget this. You can only look at it because it shows that if the RHS is part of the key, you will not be able to split the relationship. This is what we have shown here. Okay? For example, if you see this thing here, AB functionally dependent C functionally dependent A is no part of the key. You can see that. Okay? By this definition. It is real. Okay? Because of this definition. The transitive dependency doesn't come into picture because if you check now, which are the keys for this relationship. Okay? Now AB is the key. The AB is determining C. Okay? So there is no other non-prime attribute that is transitively dependent on AB. So AB is the key, and according to that first mistake. Now, why is this definition important? This is important because in this case, we want to make relation into BCNF as part of AB or AC. We will get into problem. Okay? Right? For a simple reason, the dependency derivation that AB together determines C will be lost. These two relations will be in BCNF. Okay? Right? But you will not have if P is going to be here and here P. A is going to be the key. Okay? So you suddenly will have these two relations in BCNF, but for preserving this dependency, AB together will determine C. Okay? That will be lost because that cannot be no longer be a key. So we stop for this at CNF. So there is some duplication that we suffer because of dependency CTA. should make things very clear to you, in terms of how to look at these functional dependencies and how to look at 1NF, 2NF, 3NF and BCNF, giving functional dependence. Okay? Right? I think the case where we had a problem, where I think, right? If a key is constantly dependent on a non-prime attribute, then it is not in PNF. Okay? Example that I gave, A is the key, but then it is constantly dependent on C here, as you can see here. Okay? Right? So this is what actually we actually, people should be really careful when they are applying this constant dependency. Constantly dependent on a non-prime attribute. It is not directly determining. Okay? Constantly dependent. That means it is actually determining. Key determining a non-prime attribute. Okay? I guess I have to slightly rewrite this. Constantly determining. Okay? This is the other way. This is determining. Okay? Right? Then it is not in CN. Okay? Let us see one more example. I think we gave an example where we were sort of this is a case where people are arguing here, saying that this is determining C, C is determining D. So, A is determining D. Okay? Right? Then E is also determining A. But look at the keys for this relationship. AB is the key, BD is the key, and BC is the key. So, these are all part of the key now. A, B, C, D are part of the key. They are all prime attributes. Okay? Now, among the prime attributes, there is no non-prime attribute here, all are prime attributes. This dependency C to D, the D is part of the key here. You can see here, D is part of the key here. Okay? Right? So, LHS of FD, FD is LHS of the FD is part of the key. D, A is part of the key. Hence, this becomes now within PNF. Okay? This is where we are actually, so this is thoroughly in CNF, but this is thoroughly not in DCNF. Because you can see here, but then any splitting of this relationship as an exercise, just take this example and try to take this, then you will have problems of dependency preservation. Okay? Whatever way you want to split this relationship, you will get into dependency preservation problem. Right? If you split this relationship, which is CN. Okay? Any further split of this to achieve this CNF will create problems. Okay? That is the idea of this. We just summarize. Okay? What is the idea now? We will actually, every FD we will make it in terms of relational database design. Every FD, the LHS, okay, is to be a super key. Okay? This is our primary goal. This is the BCN. Okay? Right? This is our goal. Okay? But then, any split causes problem, okay, causes dependency, preservation, then we will stop at 3NF. Okay? 3NF where the right side is the super key or the left side is the part of key, we are not going to touch it. But with the dependency, FT, for example, take this FT here. if it says the left side here is not a super key, the right side is not part of a key, then certainly these two are going to be non-prime attribute. Only it becomes out or do some tricks by saying that A can be part of one relation, AB can be split into a separate table, without any problem of dependency reservation. Okay? Easy to actually bring it. Take a dependency where LHS is not a super key and also T is not part of it. If T becomes part of a key, any split is going to cause it. Tell me. That's where DNS puts this requirement that LHS has to be a super key, or if RHS is part of a key, leave it there. Okay? That's what the DNS is providing you as an example. Okay? Right? I will actually do, let me see if anybody has any questions. Okay? Yeah, something happening here. Okay? C not A to B. There's is there a mistake on the table and you can see something in the chat box. So I'm only on the which part was stuck, I don't think. Okay, right? I will do this one and also, I think for the editions, I think if there are any questions now between, I think it should be clear now. Whatever I called up to this clear for you. The simple thing why BCNS is the highest normal form where functional dependencies are involved in the attributes of a relationship. Okay? Right? CNF is a relaxation of BCNF. Okay? For the reason that we just explained. UNF, there is actually the keys are not fully determining the non-prime attribute. Only part of the key is determining the non-prime attribute. That's where we have to avoid UNF. UNF anyway is just where all the things are atomic. Okay? So we will do the, I think I have to do a little more example. So what I do is, I will just do the important Armstrong actions. But I wanted to keep the dependency preservation thing to the last. So that's where actually it is what we take. I think one of the most important things as far as the functional dependencies are concerned, which we have not done so far, is the Armstrong actions. Okay? These are the ways you can actually derive more functional dependence. As you can see here, the reflectivity is the case where if you have a functional dependency, okay, it is the first action. If AN functionally determines B1 to Bn, okay, right? And B all has the PK dependence. Okay, we will also call the reflectivity. Okay, action. What is the augmentation action? If A1 A functionally determines B1 to Bn, okay, by just adding now C1 to Ck on both sides, no, it still be valid. For example, A1 to An, it gets added on both sides. This is called the augmentation rule. What is the transitive rule? If A1 to A1 functionally determines B1 to Bn, B1 to Bn functionally determines C1 to Ck, then A1 to E functionally determines C1 to Ck. Okay? This basically is the transitive rule here. There is an augmentation rule here. There is a reflectivity rule here. Okay? Even for example, I think this is the part where I will just use the, okay, for the Armstrong actions, we will take, for example, a relation, okay. Now let us say, what first action says that there is A and B. We can say that A and B functionally determine A. This is a functional dependence. Okay. So all the rules of normal forms be functional dependency. We say, okay, for all non-trivial functionalities, the left-hand side has to be reciprocity. In fact, right, this trivial functional dependence is any number of functional dependencies. So when you want to understand what is how the normal forms are defined from their base, this is important because we say for all non-trivial functional dependencies, the left-hand side has to be reciprocal. Okay, right? So the given a functional dependency, you can clearly write lot of these functional dependencies here. A B determines A, A B D, A B C functionally determined. All these dependencies can be written. Okay? Why is this trivial functional dependency true? Why is this trivial functional dependency true? How will you prove? You have to prove this action. How will you prove this action? How will you prove this action? What is the see? That's the important understanding that you should build. You know? For example, how do you build? How do you show that a functionally deterministic way this means that given a tuple of the ring A, then there is also another tuple where A to B2. Now, if A1 and A2 are same, then B1 and B2 have to be same. Okay? Now look at this. What this functional dependency is saying? It is saying that if two tuples agree on the value of A and B, they also agree on the value of A. That is trivial, right? For example, what we are talking about is the same tuple. Okay? We are not talking about a different value. We are talking about the same tuple. If they agree on the value of A, they also agree on the value of A, not in A. Okay? Left-hand side, we agree on the value of A and B. We are also agreeing on the value of A. We also agree on the value of B. We also agree on AB because this is just a subset. If you put something like C here, then it becomes non-trivial because it shows that when the value of A and B are same between the two, what it says is if you have C1 here, if you have another tuple A1, B1, okay, you cannot have C2 here. That's what this dependency means. Because it's C1 here. If you agree on the value of this is for this functional dependency, we're writing this for this functional dependency, A, B to C. Okay. Now if there is two tuples, they agree on the value of A and B here, they have to agree on the value of C. You cannot just put what this functional dependency means. So this has to be only C1 here as per that. As far as this functional dependency is concerned. Okay? Now, if you write here A, this is trivially true. If you write B, that's also trivially true. Because if you agree on the value of A and B1 in two tuples, you will also agree on the value of B. This is a subset of the left-hand side, which you have already agreed. Okay? This is a new thing. No, this will be different. This can be proved to be trivially. Okay? This is the way you can prove all the actions. Okay? Now, augmentation rule also you can prove in the same way. For example, if you say the second action, what is the second action going to give you? The second action is trying to tell you if there is A and B. Now, if you add a C on both sides, that's also going to be true. Okay? Now, you can see, if you consider a tuple, what does it now say? A1. This one will say A1, B1, A2, the other functional dependency saying if you now agree on A1, C1, C is same on both sides, as we can see, okay? Right? This will also now determine A1, C1, B1 will determine now also A2, B2. If they agree on both the values here, it will also agree on the value of B1. This is what. We are just trivially adding this on both sides, so we will agree on it. Because the value is, no, it agree. AC will be totally different with BC because AB is already determined. Even a value of A, the value of B is determined. This is what we mean by the augmentation. Similarly, transitivity. What is transitivity is saying? If A is there, then you have BC. Now, A determines the value of B, B determines the value of C. So, if you actually now look at A, B, C here, A will fix the value of B, B will fix the value of C, and hence, even A, you will also agree on the value of C. Because two couples agree on the value of A, they agree on the value of B. By this transitivity, they agree on B, they will also agree on C, and hence they will also agree on C. Given that they agree on A, they will also agree on C. Okay? This is what we mean by the transitivity action. Okay? Now, given a set of functional dependencies, you can derive any number of functional dependencies. For example, given by these three actions, given an initial FD, okay, right? Given a set of initial FDs for relation R, then the starting set of FDs, you can now derive more FDs. Okay, given a set of FD, initial FD, okay, this is a set that we will have. Okay. Now, what is the closure of this FD? The closure of this FD is all the additional functional dependencies. This is closure equal to the closure set of FD. Apply these Armstrong actions and get a closure of these FDs. Okay, like what we got the execute closure, you can get the FD closure. Okay, right? Is that clear? I think we see if there is an example that we can take. So here, example, let us take what we take closure. Okay. Now, closure is going to be all the, if this is there, all the FDs that come now, FDs that see. This is the transitivity action. Okay. Right? Now, you can also put, for example, through the augmentation one, AB now determines, okay, CB. Okay. Now, through this, once you add this, if there is something else that can be determined, for example, if there is a this thing that says CB determines, let us say D, then once you have this determines D, AB determines CB, CB now is determining D, then you will have AB now determining, okay. Now you can start adding all the, this came because of the augmentation rule, okay. This is coming because of the transitivity again. So you can start determining this, okay, using the Armstrong actions, okay. You can apply transitivity. The first one is applied transitivity. The second one came because of augmentation. AB and which one did we have? So AC. We have put right now on this augmentation rule. AB determines CB. Then we have a CB determining D, so this again came to transitivity. Once this FD is there. Okay. Now the FD class closure will give all the set of FDs that are applicable on this relation, given an initial set of FDs. Okay. Right? Now given this, you can see now CNF definition. This is where I wanted people to hold on because the transitivity dependencies are part of the Armstrong action. Okay, you can virtually have a lot of other FDs coming in because of the transitivity dependency that are part of this action. Okay, right? Okay. Now, how is the relational database design done? Okay, given a relation R, now I will show you how exactly the relational database design is done. Now that we know FD closure also, this is the okay. The initial set of relations come from ER model. Okay, right? This is the relation. Now, what you do, you actually look at the FDs, set of FDs defined on these relations. This is the initial set. Okay, right? Now we are going to determine if R is in PCNF. Okay, given these FDs, now whatever these are actually, there could be a lot of FDs that can be derived, but then whatever initial canonic form of FD, that is, the full set can be derived through an equivalent. You can say it's an equivalent set for this FD. If you have a closure, F closure that we have defined in this case, right? FD plus. The initial FD is called the canonical FD, because this FD is actually obtained by this an initial set of FD, and this is complete. So in some sense, canonical form of the FD, this is a complete FD plus. All the other FDs that can be derived from this set of FDs is what we mean by the FD plus. Okay. Now determine the relation. Okay. By applying functional dependency, the left hand side, non-trivial functional dependency, the left hand side is a superposition. If it is not, then what you are going to do is try to split the relationship into R1 from R2. Okay, whatever. Okay. Let us consider here R1, R2. Okay. Right. Now, when we split it into R1 and R2, there are two things that needs to be worried about. The display is lossless. Okay. And it actually preserves. Dependency. Okay. If the split is lossless, which means that you won't lose any of the tuples in R because of the split into R1 and R2, this is fine. So this is a necessary condition. The split has to be a lossless one. Okay. The second condition is this, that the split preserves the dependency. All the original FDs defined on R have to be preserved on R1 plus R2. Then only the split makes sense. Otherwise, the split, again you have to join both R1 and R2 to actually ensure that the dependencies are preserved on the okay. It becomes a costly effect for you to preserve these dependencies. Okay. For the split to be lossless, one of the conditions is R1 intersection. I can't get these people. Okay, so I was just writing R1 intersection R2. That means there are some common set of attributes. Okay, and then either R1 is to R2. Okay, this means the split should be such that there are some common attributes between R1 and R2, and then they actually functionally determine one of the relations. Okay? In which case, the split is going to be lossless. In this case, the split is going to be lossless. Okay? That means the dependency, see, you need a common attribute. For example, take a case where the initial thing is A, B, C and D relationship. Okay? Now if you split this relation into R1, A and B, okay, and R2 into, this is a simple case, C and D. There is nothing common here. As you can see, fully cross product is possible between R1 and R2, which will not preserve the original now. Unless everything is independent of everything here, in which case actually it is a wrong in this relationship. Okay? In which case this this can be done whatever way you want. For example, there are dependencies across these relationships. Then what you need to do is, for example, imagine that there is a case where this is the case where we are going to look at how we, let us imagine that there is A, B, C, D. Okay? We know that A is in this case. So suddenly, there is no other key in this functional dependence. I am giving only simple case. Now let us say there is a dependency to D. Okay? Now we know that this is not going to be, this is not in B because the C determines D causes this violation problem and this can cause duplication. Now suddenly we are going to, now look at how we are going to create this. Keep, for example, the one that is violating A, C, D. Suddenly both C and D cannot be kept into the same table along with A. Determining both and C and D also determining both. Without C being a key, it cannot be D. Okay? Now you can split the other one into saying that C and D. Now for this to be, now if you split it like this, okay? Now there should be a way by which what this is saying is, you can see here, what this is saying is, the C, the common attribute C, okay, across R1 and R2, determines the D. Now you can see A determines C in this particular table, but C is also, in place, which is key. Now any joining of R1 and R2, because this is key, now you can see this value actually joins with whatever values that are present here, will produce original table having key. Okay? This is what we mean by the lossless property. Okay? Right? Now what is the dependency property? Now, as you can see, there is a dependency here saying that A to B to C to D. Okay? Right? Now, if the dependency that A determines through, I think, example cases where we can also take certain, the argument becomes slightly more complicated. Okay? Where basically, if you say that A determines B, C, and C determines D, and then A is still the key because A is still not the key. Okay? I think we have to keep this D here. Okay? But then, if you want to see the dependency preservation by this split, okay? A is actually determining B, C, and D. Okay? This split that C is now taken off. Right? Now, if you see what are the part of R1 and what are the original dependencies, this can be written as, these dependencies can be written as A determines B, A determines C, and A determines D. Okay? Right? that is the and then C determines the D. Okay. So this is basically determining all these things is what we are seeing. Okay. Now you can take this attribute A, B, C. What are the original dependencies that were actually there in the FD should be preserved. Okay, should be preserved on this relation R1 A, B, C. Okay. Now A determining B, A determining C are preserved in this relationship, and those are the only attributes that are part of this. Okay. Right. Now, if you take the C and D, it is also preserved. The dependency now, which is A, actually determines D. Okay. This is not preserved. Here. Okay. It is not preserved in this way. Okay. The A determines the D preserved in this way. The only way this dependency can be preserved that A determines D. Okay? Now, since A determines this C here, okay, C is the D thing. Since C is common now, C is going to preserve this dependency. A actually determines the D. Okay, because this actually the C determines D. Also determines, okay, C determines D, also implies that A determines the D here. Okay, that is original dependency that we have C determines D, also implies that A determines D is preserved in the switch here. Okay. So since this is preserved because A determines this dependency is it's also dependency preserved. Okay, right? This is dependency preserved. Okay, this is what we mean by taking the F closure, taking all the functional dependencies, and then seeing that given a relation R, if you're splitting it, looking at whether all the dependencies, the lossless property is obtained by actually making sure that this is the intersection of R1 and R2, which is either R1 and R2. This split will give the lossless property. The second one is, if you want to preserve the dependencies, then you have to compute the FD closure, and you have to, from the FD closure, you have to get all the dependencies that are part of the FD closure for that particular attribute set, and see if they are all preserved in that in that split. Okay, I think this is to be given an example where the split may not actually preserve the dependency. Okay, right? For example, the case where the dependency cannot be preserved in the simple case where we take R, A, B, C and say that A, B together will determine the C. Okay, right? Now, whatever way you will split this one here, it's not going to be actually the case where R containing A and B, okay, R1 containing A1, AB, then R2, BC or AC will not preserve. Okay, right? This will not preserve the dependency because you can see the original dependency is on A, B, and C. None of this, that dependency cannot be, even A and B, this dependency can never be preserved. Even A and C dependency can never be preserved because you need B to actually preserve this dependency. A and B together are determining C. Right? So if you just have A determining B, okay, and B determining C, then that's possible for you to actually do this. Okay? B determining D can be easily this dependency preserved. Okay, it's easy to see this split actually ensures dependency preservation. So the original table can it still is split into this for the dependency preservation, right? And since there is also common attribute B, the intersection of R1 and R2 actually determines C. The B determines C. This is also lossless. Okay? Both in this place, both lossless property and dependency preservation are obtained by this place. But the minute actually you make it A determines the C, then the dependency preservation is not possible. Okay? In this place, and whatever we do, we would I think should conclude what I'm seeing as I can do some examples. Okay, as part of this I can do some examples. So why this is so how we would basically would like to work on the complete quick case in the next class. We will take a set of examples, then start solving those examples to make it more clear for you. But in this class, since we actually not had a class on Saturday also, I will try to finish the 4NF, which is a multi-value dependency. In this, I will be actually stopping with functional dependency. Okay. Are there any questions on this? Any questions? Otherwise, we will take multi-value dependencies and stop there in today's class. Okay? Yes. Okay. We see the multi-value dependencies and the joint dependencies, and then stop there, and that should actually normalization and relational database design. Okay, right? And then we will possibly look at some tutorial. I tutorial sheet, and I give you tutorial, and then I try to solve these tutorial problems on one of the classes. Okay, so that it becomes more clear for you in terms of the tutorial sheet. As we do the tutorial sheet on this, I will do only one tutorial sheet on this, and another tutorial sheet on the indexing structures. Okay, two tutorial sheets I'm going to do for you. Okay, right. So what is the multi-value dependency? Multi-value dependency, as you can see, I've just taken a simple example which you can understand. Okay. Now take the set of attributes here. Movie star, address, movie name, and here. Okay. And again, I took the famous, this is very famous in Telugu, so I'm taking the star notes. Now let us say this Mahesh Babu has actually two addresses. These are nothing to about. I don't even. So I'll just put this for us. Okay. You can see, let us say the star has two addresses. He has two houses in Hyderabad where he can stay. For example, this 303 Gachikauli and another address is 405 Kachipura. Okay, right? Now you can see Mahesh address. Now let's each movie name is some name here. I don't know whether this is correct, so don't take the DS as the name. The scientific not correct. So this Guru is famous with me. Let's say in the year 2009. Now it is also now I have to repeat this for the other address of Mahesh, 405 Kachipura, 205. Okay? Now you know, even that you also now see what to do. Okay, another movie. You also have to add here. Okay, automatically that for this star, this also will come. Okay, we know that even that he has two addresses, right? Multi-value dependency. Okay, Kachi, we are actually complete for this. Okay. should dependency even S see given my age no and this is what is called value dependency. As there is a multiple even a star we know it's only one case he is going to be in. Okay, that becomes functional dependency. Now here it's a multi-value dependency. Okay, now you can see multi-value dependency is the general case of a functional dependency. When if we limit this value to 1, okay, can have multiple values in a single value. Given my age, so far we have examined all the relations, they are only functional dependent. We need to examine the case where there is a multi-value dependent. Okay, this is the case of a multi-value dependent. Okay, right? Now, multi-value dependency is the general case of functional dependency. Okay. For example, star and address in two-value dependency. If the star has more than one address, I'll give this we stay only in one address. Okay? So every functional dependency is a special case of a multi-value dependency. Now, in your relation, there are no multi-value dependencies. Then 4 and F won't come into picture. 4 and F will come into picture only in case. Also, another example for multi-value dependency can be, let us say there is a database course. Okay, course. Now there is an instructor. Okay, book. Okay, right? There, this course. Then there is an instructor. Book. Okay. Fourth. Number. Okay, let's say the 4. And like the same one has want to say course to database. Okay, it is course. Say now there is a teachers who can this course. Okay. Now this is this becomes the two-value. Okay. Now there is a set of people who can course. Okay. Both of these people can teach probably a base. Okay? Then let us say that the book. Okay? Now book. You can say now you can say or you can now easily see what are the core database then access book. Okay. And also we have database in B. And you have to actually repeat what? Same thing with finance. So you can see this is an example of multi-value. Multi-value dependency. and then force to actually, as you can see here, force by you find that now this instructor teaching this, the instructor and the book, we use all the books. So the multi-value dependency, right? So this is another case of a relay having multi-value dependence. Okay, right? Even an MPD, okay, and then the books, then force title will functional in the instructor and the book. In this particular case, force title to instructor is a multi-value dependency. Force title to book is a multi-value dependency, an NPD. So an NPD has to be treated differently. Once you have an NPD, you're going to say the left side of the MPD has to be super key for it to get the normal form. It's no longer functional dependence. It's a multi-value dependence. Okay? Right? Right. Now, for completeness sake, I will also show you what is that joint density. Okay? Now the joint dependency is what we say is given a relation, okay, given a relation A, B, C, E, we can say there is a joint dependency now between A, B, E is that. Okay, the joint dependency says that when you split this relationship into A, B, and and say that A, B, whatever, and say whatever joint dependency. Okay, this relation becomes, if you split this relation into A and B, and relation into A and C, and join these two relations, you will get the original relation. That's what the joint dependency says, that this relation R, for example, as an example, we take, for example, this table as consisting of what? E, some setup. Okay? This you have to put it in A2, B2, B2. Okay? We have some set of tuples. Okay? Now A3, E, B3, B3. Okay? Now there is some set of tuples in R. Now take the AB of this and take AC of this. Okay? Now if you join both these R1 and R2, you will get the original table. In which case, we will say that there is a joint dependency in this relationship. If there is a joint dependency between AB and AC. That's what we mean by a joint dependency. A joint dependency can be seen as a more general case than the multi-valued dependency. For example, the multi-value dependency can be written as a joint dependency by saying that, let us say we have a multi-value dependency between the previous case, okay, between A and B, okay. Right? You can say it is equivalent to a joint dependency by picking A, B into one and A and rest of the attributes. Yeah, good. This is how the joint dependency. As you can see here, AB gets represented in 1, and the A and the rest of it will come as the rest of the attributes. And now you can easily see that this can be expressed, an MVD can be expressed as a joint dependency. If there is joint dependency, you can split the relationship into RAB and RAC, and then this is what we call as a quick form. Okay, right? So once you have a joint dependency, that can be split every multi-value dependency, the way you split it. Okay? The same thing you're going to do with the joint dependency. So if you want to actually understand the functional dependency is the FD is the. Okay? This is the lowest level. A more general case is FDD. So this comes up to BCNF, what we consider as BCNF. Okay? Now, a more general case of NVD is that comes as a, if NVD is present in your relation, it comes as a 4 and that. Okay? And if a joint in your relationship, then it comes as a 5. Right? This is increasingly more general case. Okay? Actually, in the specific case of an NVD, in the specific case of a joint dependency. What we are trying to say is the relation is such that the executes the relation is such that there is joint dependency present. Okay? In some sense, as I said, we can express an NVD as a joint dependency, FD as a joint dependency. That's how this is actually comes to. Okay? The functional dependencies, okay, are being expressed as part of dependency. Okay? Right? This is pretty frequent of the normal forms, except that we have to. Generally, people don't go into 4.5 and 5 because of these dependencies. The easiest thing are the functional dependencies in your data. Only in some cases you deal with NPDs, multi-value dependencies. Joint dependencies are generally ignored because they are very hard to research because they come from the domain and it's not easy to discover what are the joint dependencies that are present in your relationship. So this is much harder to reason with joint dependencies, and normally this is ignored. Okay? So there is no much basis for reasoning with joint dependencies. There is both functional dependencies to some extent and NVDs are available for sound mathematics as we saw. So I think what I'm going to do is I'm going to stop here. I will now see where actually I'm not going to deal with the normal forms. I'm going to deal in the next class with relational algebra. Okay? I'll have a tutorial sheet which I'll circulate. I'll actually do a tutorial sheet. Right now, I will give a couple of questions in this class and see if we can answer from it. Okay? Right? See how many can answer from here. Or is this false?
It's false.
This is suddenly false. Why is it? You start thinking now. The idea of this is to make you think, right? So how will you prove? Okay, let me ask one more question. Okay, I'll come back to this and to I did this and then stop here. See, and the FD is AB determines C determines B, A, D determines A. What are all the FDs that follow from this? All non-female FDs. Don't put the female FDs. What are the female FDs? There is some key there is. Third is 2. Why is the third 2? Linear campus. Why is 2?
third one is also false. Combination
AB are determined in C. Does it mean A determines C or B determines C?
Department staff.
Huh?
Okay. CSC department. Staff ID 1 to 3. Mechanical employee ID 1 to 10.
Does this mean
Department
a couple agrees on the value of A and agrees on the value of B?
Teacher
Okay.
and
They
department
together, they agree on the value of A and B. Then they agree on the value of yes. B legally do not determine B. That's correct. Partner and answer third. So will you modify your answer for this? Will you modify your answer? Okay. Or will you go by what you say? Third is what? Will you modify your answer? Take this here. What does this mean? It means you can understand what is the meaning of the function independently. What is saying is A1, B1. You can easily construct A1, B1. Okay, if there is another A1, B1, you should agree on a C1. Okay? You can easily have, for example, the statement and block. So we easily have value A2 B1, okay, which will be some C4. Now you look at this. They agree on the value of B1, B1. Will they agree on the value of C here? That's what this implies. If they agree on the value of B, they should agree on the value of C. This is only saying that if they agree on okay, important for you. Okay, right? And then use that understanding for doing all the constructing all the rest of it. What is function independent? In this system to understand that. And use that, building all on top of it, whatever we have done. Given they agree, we know that the left hand side of there the aspirated for T. Because the agree will make otherwise the data in your table. Okay. Right? Given these are things, use the constant actions to determine a lot of other FD. Okay? Now you want to split it, make sure that your split is lossless, the split is preserving the original function dependency. These are the basics for doing the DSP. I will do couple of more problems in the next class. No, it's possible. Okay? Couple of three problems. We do the full calculations and we'll show you how to build them in the CCNS, how you're going to split it, keeping both files.
A department ID, B faculty ID. ఆ రెండు ఉంటే ఏ సబ్జెక్ట్